We present our work, NeRF Revisited, Fixing Quadrature Instability in Volume Rendering, where we introduce PL-NeRF that revisits the quadrature used to approximate the volume rendering integral in NeRFs and derive the rendering equation under the piecewise linear opacity assumption. NeRF, or neural radiance fields, tackle the problem of novel view synthesis given only images with known camera poses as input. The model takes as input a 5D continuous coordinate and outputs the volume density and color at the corresponding point. One of the key underpinnings of NeRFs is volume rendering. That is, it allows for end-to-end differentiable learning of 3D geometry and appearance from only 2D images. In this work, we dive into this volume rendering equation independent of the model, the input, or additional loss functions. The formula that we've all gotten used to takes the following form, and this comes from the continuous integral as follows. That is, a pixel's value is the expected color along the ray, where the probability density, PS, is given by the volume density multiplied by the transmittance. Since evaluating the continuous integral is not analytically possible in practice, it is typically approximated with quadrature, resulting in the expression that we are all used to. That is, given n samples along the ray, a sample falling in the interval Sj and Sj plus 1 has the opacity tau j, resulting in the quadrature illustrated with the green rectangles. And this leads to the volume rendering equation that we were all used to, which is equivalent to the exact integral under the piecewise constant opacity approximation. Different from classical rendering works that use the volume rendering equation to render an image given a scene, NeRFs instead optimize a scene given a set of training images, which bring up certain issues under the piecewise constant opacity assumption. We dub this problem as quadrature instability. To illustrate, let's say we are given this chair scene. With these samples from the blue training camera, the sample marked in dark blue would be trained to have high opacity, as it is the sample right before the object surface. Given these orange samples from the orange camera, this sample would peak in opacity. However, given a different set of yellow samples at a different training iteration, this other sample would peak in opacity. This shows that the piecewise constant opacity causes sensitivity to the choice of samples. This leads to conflicts in ray supervision. Under the piecewise constant assumption, to render perpendicular rays, the model has to store optical properties at a region in front of the surface, as a sample takes the value of the left bin boundary. In the presence of a ray near the grazing angle, it will be crossing this region of high opacity, associating it with conflicting opacity and color signals, resulting in fuzzier surfaces and blurrier renderings. Moreover, it is also common practice in NeRFs to draw important samples via inverse transform sampling. However, under the piecewise constant opacity assumption, the CDF is non-invertible. Concretely, a piecewise constant opacity leads to a piecewise constant PDF, which implies a CDF that is piecewise constant but not continuous, and hence it is non-invertible. A surrogate function is needed for important sampling, leading to imprecise samples, as it does not result in samples from the actual ray distribution. Now let's try to do better, by instead of using a piecewise linear assumption to opacity. We first show a general form for Pj, or the probability of the ray terminating at interval Sj to Sj plus 1. We show that this is in closed form for all piecewise polynomial approximations for opacity. A polynomial of degree equals 0 is the original piecewise constant assumption, which leads to quadrature instability. To justify our choice of linear, we further show that for degree greater than or equal to 2, it leads to poor numerical conditioning. That is, when samples are close to each other for higher degree polynomials, it can give negative opacity values when interpolating. Thus, we use a quadrature under a piecewise linear assumption for opacity, given as follows. This is illustrated by the orange trapezoid as shown here. Under this assumption, we get the following simple and closed form expressions for Pj and transmittance, resulting in a simple modification to the volume rendering equation. Moreover, The piecewise linear opacity leads to a piecewise linear PDF, which results in a continuous CDF. Since the CDF is increasing and continuous, then it is invertible. Hence, we do not need to use a surrogate function. Specifically, the CDF can be written as follows. From here, we are also able to derive a closed-form unique solution for inverse transform sampling, which we call our precise importance sampling. And this also leads to more effective supervision on samples such as depth. As shown, our precise importance sampling leads to a peakier PDF and a sharper CDF as we are drawing samples from the actual ray distribution. Here we show some results. We see that our approach alleviates ray conflicts. That results in less fuzzier surfaces, and crisper textures. We show that our simple modification quantitatively outperforms the constant baselines across all scenes in multiple datasets. And we also achieve better qualitative results. Our approach is also able to achieve better geometry extraction, as shown by the holes in this Lego scene. That is also backed by quantitative numbers. Lastly, we show that our approach is a drop-in replacement to existing NeRF-based methods, such as MIP-NeRF. And we also show that PL MIP-NeRF gives crisper texture and also less fuzzy surfaces. Quantitative metrics also show the advantage of our PL MIP-NeRF. And we further test our approach on a voxel-based method and also show consistent quantitative improvement. Thank you.